The role of temperature on defect diffusion and nanoscale patterning in graphene. This manuscript was published in the journal Carbon in 2022. Graphene is of scientific interest due to a variety of unique properties, such as ballistic transport, spin selectivity, the quantum Hall effect, and other quantum properties. Nanopatterning and atomic scale modifications of graphene are expected to enable further control over its intrinsic properties, and use of a scanning transmission electron microscope, or STEM, for this purpose has been promising. The STEM e-beam has been used to remove atoms, enabling milling, doping, and deposition. These processes are driven by ejection of carbon atoms from the graphene lattice. However, a detailed understanding of beam-induced processes and the subsequent cascade of after-effects is lacking. Here we examine the electron beam effects on atomically clean graphene at a variety of temperatures ranging from 400 to 1,000 degrees centigrade. The original intention was to see if we could reliably create single atomic vacancies at any desired location in the graphene lattice. What we found was counterintuitive and surprising. We began by automating the milling of holes in graphene using an accelerating voltage of 100 kV, which is above the displacement threshold for carbon atoms in graphene. The automation enabled us to perform repeated experiments with the same experimental parameters to gather statistically meaningful datasets. When attempting to mill a hole, the beam was scanned in a small spiral around the desired hole location. This generates a small circular image with each pass, and the average intensity of this image can be tracked through time. As the hole is milled, the image intensity drops off, and when an adjustable threshold is hit, we consider the hole completed, and the beam automatically moves to the next position. With this approach, we can automatically mill arrays of holes. We performed this milling procedure at various temperatures, and here we plot the average dose required to mill a hole. What is surprising is the unambiguous increase in dose required to mill a hole as the temperature increases. To get a better sense of this effect, here is a comparison of the perfect graphene lattice at 900 degrees after having been irradiated with 10 to the 10 electrons per square nanometer. In contrast, at room temperature, with about an order of magnitude less dose, the graphene is almost entirely gone. What we expected, and what theory suggests, is that an increase in temperature should assist atomic ejection, and is the opposite of what we observe. To understand what is happening, we performed another experiment where we milled a hole at the center of the field of view and took sequential images of the surrounding graphene during the milling process. What we observe is that a chain of defects grows into the frame, branching toward the milling location. Only when this defect chain reaches the milling location do we form a hole. What is happening is that we are, in fact, generating many vacancies as we attempt to mill. But at elevated temperatures, single vacancies rapidly diffuse away from the milling location. These vacancies have some probability of meeting in the graphene lattice and restructuring into a divacancy. This new structure does not diffuse significantly at these temperatures and therefore becomes fixed in the lattice. Defect chains are built up of these diffusing single vacancies. We then performed molecular dynamics simulations to capture this process theoretically. In these simulations, we can see a stepwise increase in energy with each atomic ejection. Likewise, with each merging of the vacancies, we can see a distinct decrease in energy as the lattice restructures, and we see the same defect chains emerge in the simulation. With these simulations, we can also approximate the increase in the diffusion constant for a single vacancy as a function of temperature. Here we have made this approximation for a few temperatures, the data points, and then fit the Arrhenius equation, the line, to the data points to give an approximation for other temperatures. At room temperature, vacancies are frozen in place, but at higher temperatures, diffusion is increased by many orders of magnitude. Finally, we present a simple model that qualitatively recreates the behavior of the hole formation process based on the proposed governing mechanisms. The qualitative agreement of this simple model with the experiment suggests that most important factors have been identified. This work gives new insight into atomic ejection and graphene milling at high temperatures. The results are counterintuitive but will be valuable for future efforts toward atomic scale fabrication techniques with graphene and other 2D materials. Links to the publication may be found in the comment section below.